So we'll now write down length of common chord. So suppose if two circles are intersecting and the common chord is some PQ, let's say how to find the length of this chord, given that the centers are some A and B. So we can join A with P, A with Q, this is R1, B with P and B with Q, this radius is R2, and we can join P and Q, you'll get the common chord. And usually this will be perpendicular. We'll be proving this later. That is, the line joining the centers is always perpendicular to the chord. This is a property. So if two circles are intersecting, the line joining their centers is always perpendicular to the common chord. So when I do radical axis and all, I'll explain the proof. But right now you can remember it. This angle will be 90 degrees. Okay. So if you have to find the length of the common chord, basically what do you do? If these circles are given as some s equals 0, s dash equals 0, when you subtract them, you will get a line s minus s dash equals 0. This line L is PQ. So L equal to 0 is equation of PQ. So basically, if you subtract the circle equations, you'll get the equation of common chord. And once you know the equation, you can find the distance from center to that line. Suppose if this is some D1, you can find the distance AM. That is D1 is the AM distance, which is the distance from A to this line. If you know the equation of the line, the circle is given means you already know the center. You know how to find the distance from point to a line. So the distance from A to the line, PQ, you can find out that is D1. So you can do it for the BM also for second circle, but anything would be fine. So let us do it for first circle. And once you know that M is the midpoint. So if I want PQ, it is 2 times of PM. And the value of PM I can write by Pythagoras theorem for triangle AMP as root of R1 square minus D1 square. So R1 will be known because you know the circle. And L is known because you subtracted the equations and got the line. So if you know that line, you can find the distance from center to that line, that will give D1. And if you want from the other one, you can find that would be D2. In case you want to use it for other circle, you can also write 2 root of R2 square minus D2 square also would be fine. Where D2 is BM here. You can use this method to find length of common chord. So later when we do radical axis, I'll explain why this angle is 90. And also we'll understand when you subtract these two, we're getting this line about that also. Right now, you can just note this. So whenever two circles are intersecting, subtracting their equations will give a line that will refer to the equation of their common chord. So here I didn't choose them as orthogonal circles. I'm not assuming that the radius of the first circle is a tangent to second. So I'm not taking the radius as tangent, but you can have orthogonal circles for which that can happen. But here I took it different. So the tangent at P is different from the radius. So if you draw tangents, there'll be these lines. They're different from the radius. They're not the same. Let's say, for example, I assume this angle is theta. So the tangents include theta here. So we'll try to connect theta with this result. That's why I mentioned it. So I'll do that. So what is D1 plus D2 here? AM plus MB is actually the distance between centers. So I can say if AB is the distance between the centers, we usually represent with D, which is D1 plus D2. And already we wrote a formula cos theta equal to D square minus R1 square minus R2 square by 2R1R. We already know this result also. So we know this result for the angle theta, and D is D1 plus D2. And you know the value for length of the chord also. So you can try to connect all of them. So if you are equating this, we had a result. R1 square minus D1 square equal to R2 square minus D2 square is the result which is already known to us. So this is because the PQ can be written like this or like this. So we already know this result. So from here, D1 square minus D2 square is same as R1 square minus R2 square. We have this result. Okay. We have one more result here, and we also have D equal to D1 plus D2. So you can connect and involve theta if required in the problems. So we'll not combine and make any new formula now. But in general, when you have to do any problem, you can also connect it with cos theta because D is there, which is D1 plus D2, R1 and R2 are also connected. So you can connect and do the problem. So we'll not derive any separate formula. Just if you understand this, it's enough. Only for orthogonal case, we'll write a formula, not for this case. So now we'll just write the same thing with orthogonal circle. Length of common chord of orthogonal circles. Length of common chord of orthogonal circles. So if the circles are orthogonal, the radius of one of them will be a tangent to the other. So this radius will be tangent to second one, and this radius will be tangent to first one. This angle will be 90 for orthogonal circles. This is R1, R2, and this is D. So we know that D square is R1 square plus R2 square because they're orthogonal, but I want to find out the length PQ, the length of the common chord. So you can join this also. And APB and AQ will be congruent triangles anyway. So here also it will be 90 only. So what I'll do, let us assume that this angle is some alpha. Then if this is 90, this will be 90 minus alpha. This will also be perpendicular. So what is sine alpha value? We'll use trigonometry here, equal to, suppose if I take this as M, this is X, this is also X because there is a midpoint. So sine alpha is X by R1. And from triangle PMB, what is the sine of 90 minus alpha? X by R2. So this will give cos alpha equal to X by R2. This is sine alpha equal to X by R1. What do you get by squaring and adding? Sine square alpha plus cos square alpha equal to X square by R1 square plus X square by R2 square. Now let us write the sine square alpha plus cos square alpha as 1. So we'll get 1 is equal to X square is common into 1 by R1 square plus 1 by R2 square. So find the value of X from this, and the common chord will be PQ, which is 2X. So the value of X that you get will be R1, R2 by root of R1 square plus R2 square when you simplify that above result. And the length of the common chord will be 2X, which is given by 2R1, R2 by root of R1 square plus R2 square. So if two circles of radius R1 and R2 are orthogonal, the common chord of that has a length given by this formula. You can remember this as direct straight away standard result. So then we have the concept of intersection of two circles. Or you can use the word relative positions of two circles. That would be better. Relative position of two circles. So the first case in this is, there are two circles which are non-intersecting circles. So here we have to write down the condition that two circles are non-intersecting. So if A and B are the centers of the circles, let's say this is P, this is Q. So clearly AP is R1, BQ is R2, PQ is unknown. So the distance between the centers AB is suppose denoted by the symbol D. It is equal to AP plus PQ plus QB. So clearly, you know, AP is R1, PQ is unknown, QB is R2. So it's R1 plus R2 plus PQ. So clearly it states that this is more than, D is more than R1 plus R2 because there's R1 plus R2 plus something. Obviously, D is greater than R1 plus R2. That means we can remember the condition whenever you get distance between the centers of two circles greater than sum of the radii, what will you conclude? The circles are non-intersecting. So in this case, we conclude circles are non-intersecting. What is the criteria for that? D should be greater than R1 plus R2. We conclude that circles are non-intersecting. And after that, we'll also write down the number of common tangents. So usually you can draw two tangents which are common like this. They intersect somewhere here. They are called direct common tangents. Better I'll draw it in a different diagram. So there will be total 4 tangents. 2 are called direct common tangents. 2 are called transverse common tangents. I'll redraw it. So we can draw 2 tangents like this, intersecting outside the line joining the centers. And that point is collinear with A and B, but it's outside AB. So this is C2 is the point where direct common tangents are intersecting, and that is called by the name external center of similitude. And you can draw 2 more tangents like this, which meet in between them, C1, which is between them. So this is called internal center of similitude. So total we can draw 4 common tangents. These 2 are called direct common tangents, and these 2 are called transverse common tangents. So number of common tangents, if I ask you, answer is 4. And in particular, if I say number of direct common tangents, you write in short form as DCT, but right now I'll write direct common tangent completely. The length number of direct common tangents, that is DCTs, you can say in short, is 2. And number of transverse common tangents, TCTs in short form, the number of transverse common tangents is also 2. TCT in short form, this is 2. And what is the point where direct common tangents meet? C2 is called external center of similitude. C1 is called internal center of similitude. So the point of intersection of DCTs, direct common tangents, is known as, is denoted by C2, which is collinear with AB, which is collinear with the line joining the centers, which is collinear with line joining the centers, and is known as, so you just use the word, is collinear. So the point of intersection of direct common tangents denoted by C2. So it is collinear with the line joining the centers and is known as external center of similitude. This is called by the name external center of similitude. And similarly, the point where transverse common tangents meet, the point of intersection of TCTs, transverse common tangents, is denoted by C1. It is collinear with A and B. It is collinear with the line joining centers A and B and is known as internal center of similitude. And is known as internal center of similitude. And is known as internal center of similitude. C1. And we have two important properties. That is C1 divides, the internal center of similitude divides AB, the line joining A and B in the ratio R1 is to R2 internally. We have a proof for that. I'll show in the diagram anyway. So that means if you know the centers are some x1, y1 and x2, y2. So the internal center of similitude divides in the ratio R1 is to R2 internally. So if you have to find it, you can use the section formula and write that as R1 x2 plus R2 x1 by R1 plus R2, comma R1 y2 plus R2 y1 by R1 plus R2. So you can write it by section formula. Similarly, C2 will divide AB in the ratio R1 is to R2 externally. And if you have to find C2, it is collinear with this, but it is outside AB. So if this is x1, y1 and this is x2, y2, and if C2 is dividing it in the ratio R1 is to R2 externally, you apply external ratio formula, then it will be R1 x2 minus R2 x1 by R1 minus R2, comma R1 y2 minus R2 y1 by R1 minus R2. This is the formula to find out external center of similitude. But why is the ratio R1 is to R2 will decide that. So if you just go back to this diagram, so if you have to find AC1 by C1b in this diagram, it will be R1 by R2, and AC2 by C2b is also R1 by R2. So basically you see that C1 will divide AB in R1 is to R2, C2 will also divide in same ratio. One is dividing internally, the other is dividing externally. Then we have a word called harmonic conjugate. You can say C2 is the harmonic conjugate of C1 with respect to AB. So in such a case, we use the word harmonic conjugate. So why is this ratio R1 is to R2? If you have to prove it, let me just draw the diagram again. Suppose if I'm choosing the direct common tangents, so this is 90, we already know. You join this, these points are collinear. So clearly you observe, if I name this as some PQ and RS, this is R1, this is R2. The triangle PQC2 is similar to triangle APC2. They are similar triangles. Because you have 90 here, 90 here. These two angles are same. This is a common angle. And for this small triangle, big triangle, you have two angles same. They are similar. Because if two are same, third will be anyway same. And the corresponding sides are in the same ratio. So I can just write, if I want to write the corresponding sides ratio, I can write AC2 by BC2 for bigger by smaller equal to PC2 by QC2. That is also equal to R1 by R. So from similarity of triangles, clearly we can say that C2 will divide AB in the ratio R1 is to R2. Since it is outside, we said it will divide externally. Same way you can do it for even the transverse common tangents. And if you have to find the length of direct common tangent, length of DCT. So it is same as finding PQ or RS, both are direct common tangent, they'll give same answer only. So to find that, what we need to do is just extend this line further and just drop a perpendicular like this. I'll call it as an AT. So that AT is parallel to PQ. This is 90 degrees and they'll be equal. So AT, this will also be same as PQ is also same as AT. And if you have to find AT, what you can do, you know that AB is D. And this distance will be same as R1 because AP and these two are same because these 4 points are forming a rectangle. So obviously, if this BQ is R2, this total is R1. This part BT will be R1 minus R2. So by Pythagoras theorem, AT would be root of AB square minus BT square. So we will be getting a formula root of D square minus R1 minus R2 whole square. This is the formula to find out length of direct common tangent. Yeah. Then if you have to find the transverse common tangent length, we'll again redraw the diagram with transverse common tangents. So you can draw some tangent like this, another tangent like this. These two are transverse common tangents which meet in C1. So join this and join this. So if this is P and Q, PQ is again a transverse common tangent. Again, this is R1 and R2. From similarity of triangles, clearly you see triangle APC1 is similar to triangle BC1Q or BQC1 you can say. So therefore, AC1 by C1B should be same as R1 by R2. Again, they are similar triangles. So ratio of corresponding sides is same. So clearly C1 will divide AB in the ratio R1 is to R2 and it is internal ratio because it is between them. And if you have to find the length of this tangent PQ, so what you can do is just extend this line further, or perpendicular like this, call it as some T again. So in triangle ABT, again by Pythagoras theorem, you can clearly see that AB square equal to AT square plus BT square. So from here, you can clearly see that if this is R1, this is also R1 only. So BT will be R1 plus R2. AB is the distance between centers, which is D. So D square is equal to AT square plus R1 plus R2 whole square. So from here, you will get the length of PQ is same as AT. And what is that length AT? Root of D square minus R1 plus R2 whole square. This is the formula for length of transverse common tangent. So PQ is a length of TCT, transverse common tangent. This is the formula. So once you know these results for first case, for all other cases, we need not derive. We can straight away write it.